we have today we will finish continuous time and move to discrete time in chapter 5. Hopefully, what left over in this lecture is after learning this Fourier transform, we've discussed about several, how to use the Fourier transform. So we have learned how to plot it in a frequency domain, and we will discuss how we can analyze in frequency domain briefly and do Laplace. So let's see. We have used many things. However, the conclusion is this. Basically, Fourier transform is for the case continuous time, which is the signal can be periodic or non-periodic, does not matter. Whatever it does, if it satisfies several conditions, they have Fourier transform. Fourier transform has linearity, time shifting, those properties. One of the most interesting property will be differentiation and integration. So when you do the differentiation, when you do the frequency domain, j omega will come out. If you have integration, then 1 divided by j omega comes out. So in case of differentiation and the integration, you will often see those things in differential equation. So we briefly discussed how to utilize differential equation before. So long time ago, I think when you do the engineering mathematics, you probably hear that, okay, let's solve the problem for this. And you automatically do, it will be as x plus x equals 0, something like this. And then you just solve it. So previously, when you have, say, sine omega t, maybe zeta t, whatever. If you try to solve this equation, previously what you have done before here is we have learned one method, say, is a homogeneous equation, homogeneous solution, or particular solution. So it's assuming that, okay, let's find homogeneous equation for this and find what's xh homogeneous equation and what will be their particular solution. Guessing what will be the solution for this. And then we figure out what's xp. And then finally, we add homogeneous with particular solution. That's what we have learned in chapter 2, 3, I think. So this is one way. So in this equation, first of all, all of this equation, we try to solve the differential equation given by the several variables. So in here, we assume that x consists of homogeneous equation when all of the equation equals 0, which is more, say, general solution, I say. And in case of particular solution, we guess what is the solution for this, having some variables over here. And then after adding together, if you add it together, eventually they will be the same. So that's the reason we first solve with making the right side to be 0, solve it, and then guess what will be the one of the equation and solve it. By this way, the reason that the particular solution, of course, particular solution, you definitely can find solution from here because you are guessing a solution. However, there may be more than one solution. Particular solution, you are guessing one point. But guess, all right, the left side it looks like that, right side looks like that. There may be more than one point, and they are equal. That means the particular solution may be more than one. To compensate those problems, we try to have a general solution, which is homogeneous equation, but right side is making my right side 0, and add them together to compromise that this is solution for this. However, there may be more than one solution. Homogeneous equation is not exactly solution for that, making this one 0 and final solution for that. But this one is more general term to compensate the case that there may be more than one solution. So this is one way we can find the differential equation. So this first one. The thing we can use now is using Fourier transform. So in here, in this formula, we did not do frequency domain change. We did not change the frequency domain. Now we try to change it to frequency and go back to time domain. Now, what you can do now here is, let's have Fourier transform for that. As this one is differential, we expect that it will look like this, right? And then this side, it will look like that. So, we're talking about this page 30. And then, what will be the Fourier transform for that? It's part of the equation, right? So we have a Fourier transform of sine, which is given as pi divided by j delta omega minus omega 0 plus minus j over pi delta omega plus omega 0. I guess this is right, maybe wrong. Let's see. Okay, not so bad, right? So from here, you can rewrite this left side, say j omega plus 1 x equals like that. And then we have x equals j omega plus 1 over this. And then we find a solution for that. If you go back to time domain by using the reverse Fourier transform, then you will figure out what's x. So in this one, we are not doing the particular solution and the homogeneous solution. We just find out the solution x exactly. So in short, we have first have Fourier transform, and then calculate, and then do the reverse Fourier transform going back to time domain to find out what's the answer. Of course, there's another variation you can try. Say that you divide this one to, this one is especially important when you have more than one derivation. So in this case, if you try to find homogeneous equation, you have to spend a long time to find it. But in this one, even though you look like that, if you do the Fourier transform, there will be j omega triple j omega square plus j omega x plus 1. So that looks like this. So basically, now, even though you have a higher order differential, which is, you can see in here, you can see that, okay, there was kth order. So if case 1, there will be one-time differential. Case 2, that means twice differential. Case 3, the 3-time differential. So if you have those, even though you have those differential, they only change to something like, okay, x triple, x squared, x plus 1, something like this. So they are easily can change to some polynomial equation, which we rather easy to solve. That's one of the powerful reasons that we are using the Fourier transform. So let's have more solidified form or general form for this. There's a huge number of equations in this slide. However, What you only have to remember is just two things, just two methods. So this is the general form of a linear coefficient differential equation, meaning that this is linear, right? They are just added together. Each differential term is added together, multiplied by the constant. In this side, x, which is the in sine omega 0 in this case, in the example shown on the board, x may be differentiated also, may be integrated. So if you have differentiated and multiplied by a constant, you can also show them like this. So in the meaning for this is the k means 0, there will be no differential, just y. K means 1, that means one time differential. K until n time differential. We have each of them is linearly combined. So we will often ask to, let's find out what will be the system response. What will be x versus y, which is output. One way. Wow. So one way you can do here is, we have learned this one previously. Assuming that take a look at chapter 2 or chapter 2, we have learned that when you have a system, say it has a system response, if you have e j omega t as an input, as shown in the first case, and the y will be e j omega t times system response e j omega. That's what, j omega. J omega. The frequency domain system response for this. So that's one way you can do that. You put that x like this and y like that, put into the differential equation, try to find what's h. Because if you put them, there will be a differential h for this and differential h for that. So if you have dy dt, they will given like j omega e j omega t, differential for this, h j omega, plus e j omega t, h, one time differential j omega. So you can do that. Of course you can do that. However, the second method is what we have just learned. We take this equation and then we take Fourier transform for all of these. So in case of y, if you have dk like that, k times differentiation y, and they have ak, which is a constant here. When you do the Fourier transform, we change to ak, and then j omega times k Fourier transform y, which we can see in here. So if you take Fourier transform for both sides, then they change to, we already learned that this differentiation, one time differentiation is 1, two time differentiation is 2, so j omega times y, which is Fourier transform y, and x is constant, so let's leave it. How about this side? This side, we have j omega k times x, and b is a constant. And in here, x and y don't have a relationship with k, so we can take out here h, which is transfer function for this one, is given as y divided by x, right? And then if you divide by like here, you can divide this one by this one. So there's a solution. What this one means here is, if you want to know the frequency response, or if you want to know the system response of the system H, then what you have to do here is you have sum AK times J omega and sum them together, and the numerator will be BK, which is the constant in the X, times J omega K. This is another useful tool that you can directly come from differential equation to Fourier transform. However, you can find transform using the differential equation. Okay, by far, questions? I think I should encourage you asking questions. So, should I point someone? Okay, questions? So, too clear? All right. Okay, so now we try to have an example to solve it. Of course, this is you already know it. You already know it. But this slide, I think you already know it. We have learned before. We can use Fourier transform to find the answer, or we basically already know it. However, this slide is try to formulate the process, try to make the process more obvious so that you can follow step by step. So let's bring an example. So say you have differentiation equation for, what is it, AY. Say, if you have differential equation for that, and you are asked to find a system response, what we do? Let's utilize what we have learned before. So we take the Fourier transform first. Take J omega y plus a y J omega equals x J omega. Right? This is example 4.24 in your textbook. And then we divided h J omega equals y divided by x, which is J omega plus a over 1. So very easy, right? We don't need any equation to remember. Another way you can do here is, let's use the equation shown in here. We already know that the last equation, J omega, equals summation of BK? AK, okay. AK J omega K over sigma BK J omega K. And what's AK in here? AK in here is A1 is 1. A0 is A. Right? So let's put it A1 plus A1 J omega 1 plus A0 over B in here, B0. That will be the answer for here, which is A1 is 1, J omega plus A over 1. So even though you follow this equation, they will be the same. You can do that. You can just do the Fourier transform, or you can just remember the equation and then follow it. Whatever you do, the final answer will be the same. You can do further things. If you are asked to that, okay, we want to know the system response in time domain. We don't want to have frequent domain, but we do. And then we take reverse Fourier transform, and we have learned that in here, we have learned that, just a second please. Right here, A plus J omega go back to I use my I lose my here. Here you go. They go back to E minus AT UT. Is it right? So yeah. So this is your H. So this is make you much simpler, the process. And what about the second example? Questions by far? Before we move on. So in here, we don't see many, how to say, advantage to use this. However, let's have a little bit more complicated example. Okay, let's have for example of that. This one, if you do the Fourier transform, there will be j omega square 4 j omega plus 3 times y. And then this one, j will be j omega plus 2 x. Right? Ma, are you following? No? So do you need more explanation? Yeah. So let me repeat one more time. So in here, when you have one-time differential y, its Fourier transform will be jy times y. This is a property of the differentiation. If you have 2 times y, 2 times differential of y, you can think that as one-time differential of already differentiated y. Right? So this one is j omega. Right? You do another differentiation. So there will be one more j omega. So, and then there will be j omega squared times x. Times y, I'm sorry. Times y. That's the reason if you have k time differentiation, they transform to k times j omega in this formula. So likewise, if you have j omega, because this 2 time differentiation multiplied by 1, they change to j omega squared times 1. This one time differential, so they change to j omega. 4 is constant, so 4 is here. In here, there's no differentiation, so they just change directly to y. However, there's 3 is constant over here, so 3 comes like that. Likewise, in the right side, j omega, because of differentiation, 2 from the constant. Right? And likewise, we can do the same thing over here. In AK is this side. A2 is 1. A2, which is 1, plus A1 is 4. And then A0, which is 3. Right? In here, if you have 2, we have j omega squared. We will have j omega 1. Because of this, k equals 2 in here, k equals 1 in here, k equals 0 in here, over bk, which is b1 is 1 over here, b1 times j omega plus b2, b0, which is 2. Right? So this one, you can do it this way. You can just use the equation. Either one is fine. Actually, they're basically the same thing. the more important thing is how you go back to time domain. So often in later chapter 6 or 7, I think, we will figure out how relate time and frequency. So in here, we simply divide this part to this side to find what is y divided by x. This is y divided by x. This equation, this one, how do we solve it? Of course, if you want to analyze in frequent domain, it doesn't matter. Just just do that. However, if you want to go back to time domain, what you have to do here is j omega 3 times j omega 1 over j omega 2, right? And then how we do it? Because in this form, it's very difficult to change to frequent domain, time domain. I'm sorry. So how we do it? We divide it. So we divide j omega 3 over j omega plus 1 over say a b. And what we have? A plus b equals, in here, j omega a, j omega b, which is a b times j omega, should equal to j omega times 1. Right? So a plus b should be 1. From here, a times 1, 3 times b, a plus 3b should be 2. So from here, and from here, you can find a and b, which is a constant. And we already know that in this form, we can, when you transform a constant, there will be e minus 3t ut, right? This one, e minus t ut, you can find it. So when you try to find system response of differential equation, you first take, one method you can do here is, you first take Fourier transform, take a system response. If you want to know time domain signal, then you do reverse Fourier transform by dividing them by each part, I say. So I think you already used this process a lot in previous engineering lecture. However, this is how we formulate it. We, starting from the Fourier transform, solve differential equation using Fourier transform, going back to time domain. That's how the process goes. So this is the last chapter in continuous time Fourier transform. Before we move on, anybody has a question? Nobody tried to make eye contact with me, I think. Yeah. Here? I'm sorry, there's a, like that. A plus b j omega, which is, should be same to j omega. Right? So there should be j omega. From here, a plus b should be 1. Right? Other things? No? Okay, so let's close the chapter. Move to the new chapter. Chapter 5. I think we only have, except the final exam, we only have 6 weeks left, 7 weeks left. So not many time left. So let's move on. So this one, in chapter 4, in chapter 3 Fourier series, we use both continuous time xt, discrete time xn. However, in chapter 4, we have not used xn. We only have xt in continuous time. Because in Fourier transform, very interesting point here is Fourier transform, continuous time, discrete time is slightly different. They are very close, but slightly different. I think you are more familiar with continuous time because we have seen from basic engineering classes. However, discrete time is not so popular. So let's take a look at it. So in here, this chapter 5 only dedicated to xn, which is the n is the integer. So let's remember, this is a reminder. The difference between continuous and discrete time signal is what? Let me rephrase my question. In Fourier series, in the periodic signal, we have learned that there is a difference between continuous time and discrete time. In continuous time, in signal-wise, for Fourier series only valid for periodic signal. So both xt and xn should be periodic. However, in Fourier series, not Fourier transform, Fourier series, this ak and this ak is slightly different. This one, we are integrating from minus infinity to infinite, remember? And then they are not repeating. This one has a period, right? They're repeating over one period. So we are not integrating from minus infinity to infinity for discrete time, but we only integrate from a length of n for a period, remember? So let's remember that. That means Fourier series representation of discrete time signal are finite, meaning that we are not doing the integration from minus infinity to infinite. There's no infinite is involved. If no infinite is involved, there will be no chance that this value diverge. Diverge means when you have exponential, for example, they may go to infinite, something like this. If you try to ask, okay, what's the value in x equals minus plus infinite? You cannot find the value because they are diverge. However, in this case, we only take length of n. So we can count it. There is no way they go to infinite. That means even though they go like this, because we have some number, we know that number of n, they cannot go to infinite case. Therefore, the value in here, in this case, is always finite, not infinite. That means this discrete time does not have convergence issue. We have not learned about convergence issue in Fourier series, and we have not learned convergence issue in Fourier transform yet. What it means here is like this. We assume that in case of Fourier series, we assume that we're starting from assumption that this x can be represented by this form. If you go back to our slide in chapter 3, Fourier series, we're starting from assumption that this form is existing. We did not consider the case that this form may not exist. But remember that here is exponential. Of course, it's complex. Here is exponential. And in case of continuous time, we are adding from minus infinity to infinite. We are adding infinite number of the point, right? So if the case is wrong, then there's exponential is going up, and we are adding from infinite to infinite. This may reach infinite point. So this value may be infinite, which cannot exist. So meaning that this is the one extreme case. However, mathematically wise, we say this is x tilde, which is given by this equation. Original x, let's say fx, and there is a theory that we want to make this one 0. We want to make this one 0. Of course, does not sound very, how to say, entertaining, I say, because we already assume that x, which is the signal we want to, Fourier series representation or the original signal, always have this form. We have assumption that and solve the equation. However, who guaranteed it? We just learned it, right? We did not have an image that this may be transformed to other form of signal. This one and this one is different, right? We try to find a way to change this one to this using the equation for AAK. But there's a few cases that this cannot be converted to this, meaning that this and this are different. So this one, which is the difference between this minus sigma, this one is something called error. We usually have, if error is smaller than some value, then we consider that they converge, which is error is very small. However, there's a few cases that this and this are quite different, which they cannot be the same. There's few cases in this case. One example is like that. When they go to infinite, then this one should be infinite. This one is not infinite. So they cannot be the same. This is a very extreme case. So if you go back to chapter 3, I skipped that part. And we will see a Discrete condition. 3 cases that they may not, we try to decide if you have Fourier series. What about Fourier transform? X in continuous time, x j omega is minus infinite to infinite, xt e minus j omega t dt. Right? So still, they are using minus infinite to infinite. So there's some chance that they may not exist in continuous time case. In discrete time case, interestingly enough, this one, we are not taking minus infinite to infinite. We are not taking it. We're just taking a period of n because they are repeating. If you consider a period of n, the number is finite. You can count it. They cannot go to infinite. Therefore, I once mentioned that in case of discrete time Fourier series, they are both signal and the coefficient are periodic, plus this is always exist. I cannot say always all the time. However, as this is finite, they converge to a certain value. They cannot go to infinite. That's one of the difference between these two. Likewise, in Fourier transform of discrete time, we will see similar relationship, repeating only a period of n. So we don't use infinite number. So let's take a look at it. So another review we have for continuous time Fourier transform is Fourier series coefficient. So we have used a concept of envelope. 2 kinds of things to remember. First of all, in case of continuous time Fourier transform for previous chapter, we assume that in free point domain, this is the frequent domain response we want to get it. And in case of Fourier series coefficient, Fourier series coefficient is taking samples at a certain point, right? So we have those relationships. Fourier series coefficient are samples of the envelope representing the transform. Also, on a periodic signal, I think there's a typo, on a periodic, not periodic signal can be viewed as a periodic signal having an infinite period, right? So we have learned those two. So keep in mind, and let's move on. So we try to use similar techniques. We try to find Fourier transform of discrete time. I think the mic is very sensitive. However, and to do that, we start from Fourier series having a periodic signal, and then find those envelope, and then make those period to be infinite, to make them to on a periodic signal, not periodic signal. That's how the strategy we want to have. So let's take some practice. Now, Xn is on a periodic signal, case A, which is not periodic signal. We want to find out Fourier transform for this. X tilde n is case B, which is periodic signal. We already know it has Fourier series representation. So let's take X tilde. This is very similar to what we have used in Fourier transform of continuous time. Very similar. So let's say this one is already periodic signal, and we assume that they already have Fourier series representation, which is AK given by E j omega 0 k n, right? And this omega 0, you can view them as 2 pi divided by t. So, I'm sorry, t is a continuous time, so this one should be n. Over here. So, this is we already know it, it's a Fourier series. And then, let's define a function. Let's define a new function. X e j omega. Now, we have used x j omega before. Now we are using e j omega. There's a meaning for it. So I will explain it later. If I don't do that, please remind me. So, e j omega is given as sigma minus infinite to infinite x n e minus j omega n. And remember that so in here by here, from here to here is we already learned in Fourier series. This is a new function we just defined it randomly. And let's have a trick. Let's have a trick on this. What is AK? what is AK? We have to find out that n over 1 sigma over a period xn, xk or xn? xn e minus j omega 0 kn. In here, xn should be tilde because tilde is periodic function, which is you can see in here. This one over here. So this one is definition of Fourier series. This is Fourier series coefficient definition. From here, let's do the some trick like you see before. Assume that they are not zero. They are integrating from minus n1 to n2. In this graph, we can see that, okay, we are integrating from minus n1 to n2. Of course, you can do that from here to here, there to there. Of course, you can do that. I just take the center one. So, n equals, I think this bracket means we can have any period of length of n. Whatever you do that doesn't matter. However, let's take a special case for the center one to make this one to be in here n2 minus n1 should be n plus 1 and minus 1, I don't know. So length of n. That doesn't matter. In here we are using x tilde n. Let's compare these two. Let's compare these two. We have used, in Fourier transform of continuous time, we have used that x tilde, xn are same at the center. So there's no disobeying rule. We just change this, we remove this tilde. Because at the center one, they will be the same. Right? And then, as we change this one to xn, so now we change from x tilde to xn. Xn is not valid for here. Other than that, this is not periodic signal. So even though we change the length from minus infinity to infinity, doesn't matter. Because outside of minus 1, outside of n2, there will be nothing for xn. X tilde is different. X tilde, there's a periodic function. Xn, we don't have anything, so we can change it like that. So that's what you can see in here. Xn. From here, we change to take the center one, remove tilde because they are the same at the center, make this one to infinity to make some form. And let's define a function like that. And we will use this function to solve following things. So this function is x e j omega, which is given as xn e minus j omega n. Just have a function like that. We don't have any derivation yet. Before we move on, our Fourier series coefficient, AK, are proportion to samples of x, e omega. Meaning that, if you remember this, it's similar to this one. You have a period times AK, which is this line, is when you try to take Fourier series coefficient, we take samples for that. So we can view the same thing. From here, period times AK, they are considered to be samples. If you take samples for this, then there will be the Fourier series coefficient. So that means assuming that you have E j omega, which is the envelope of this, assume that this is the envelope of this, which is a Fourier transform. We assume that we already, let's forget about this for a minute. Let's forget about this for a minute. And then we assume that x e j omega is our Fourier series, Fourier transform of the system. So they will be, looks like that, right? And then this one, which is AK, will be taking samples of this. From this relationship, you can find out that we are taking samples. So not all the point in frequency, but we are taking samples at a certain period omega 0. This is very similar to what you use in continuous time Fourier transform. So you can view them as we are taking points at every omega 0 in frequency domain. That's how it defines it. So this is what you can see in here, right here. And then, how we do it? From here, from here, this one equal to, let's rewrite k period of n, and then we can now change this AK to using this. So AK is given as this one divided by n, right? This one divided by n. So let's put it here. This is AK, and this one is still left. So we have E j omega 0 k n. That's the same thing. The same thing, which you can see in here. And then what we do? Now, to make this omega n same to xn, what shall we do? Make the period to be infinite, right? If you have periodic signal, we make the period to be infinite so that we can move other things to outside except the center one. That's same to not periodic signal. So if you make this one go to infinite, at this rate, it's difficult to find what is infinite point, because in here, of course, you can make infinite to infinite. In here, numerator, the numerator is infinite. If this is not infinite, this may go to infinite because it's exponential here. So hard to find what is the infinite point of it. So let us rephrase this one a little bit, so that in here, what is this n? What is this n? N is a period, right? N is a period, which is omega 0 is what? Omega 0 is 2 pi divided by the period. So you can do that. So now n equals what? 2 pi divided by omega 0. Is it? No? Right. So let's switch this n to here. If you switch the n to here, there will be 2 pi divided by omega 0 over 1. So if you move the omega 0 to the top, there will be omega 0 over here. Times x ejk omega 0 times exponential, which is still the same, e j omega 0 kn. Now we are adding from infinite to infinite. So now we have removed the numerator n, so we don't have to worry about those convergence issues right now. So let's think about what's the meaning of this one. What is the meaning of this one? Let's go back to frequent domain. In frequent domain, assume that we plot this function. We plot this as a function. E j omega 0 times E j omega n. Why? You may ask me why the k omega 0. Let me write them clear. Why this k omega 0 changed to omega? Why? Because remember, in this discussion we have now, x tilde is periodic signal, right? That periodic signal. Therefore, we are taking Fourier series coefficient. Fourier series coefficient can be viewed as sampling in frequent domain. So we are only taking values in frequent domain as of length of omega 0. Omega 0 to omega 0 to omega 0. So in general form, in frequent domain, those k omega 0 over here we viewed as only the point when omega equals k omega 0. So you can view them as, okay, this is the case that x e j omega, which is general form, when omega samples at point length of omega 0. So if you plot it in omega, the frequent domain, they can view it as we are taking samples as length of omega 0, taking samples, and length of omega 0. We can view it like that. And here is k times omega 0. The next point, which is k1 omega 0. So the length will be omega 0. So what will be the area for this one? Area for this one will be this yellow one, right? Which is the y-axis length times this. So you can view all of these inside this red box as those shaded area. Length of omega 0 in x, length of this much in y, making a box, multiply x and y, there will be the area. And how we do it? Making from still, we are still in the case that periodic signal. To make periodic signal to a periodic signal, we make period n to be infinite, meaning that this omega 0 becomes infinitely small, right? If you take that, you can also view them as, okay, this is area, this is area, this is area, this is area. We are adding those area from certain period. And then if you make this small, then we can find an integration. There's a part of integration. So now those red one is an area, the size of area in one box over there. And then if you take omega 0 infinity small, then we can find those line. Very similar to continuous time case. So after doing that, we will have xn, which is viewed in like this, because this one, what you do here is, if when this one you go to infinity small, there will be d omega, right? And this one, of course, k omega 0, but actually when this omega 0 is infinity small, that means there will be a certain point. You can change to omega. Likewise, in here, we can change to omega. And then, this one becomes what? Length of n. Length of n becomes what? We are taking the n go to infinite, right? N go to infinite. And what happens? But keep in mind, they are repeating in one period. So still, we can still utilize one period. One period is what in this case? Now the variable becomes omega 0. Omega 0 wise, say in time domain, they change 0 to n, for example, length of n. In frequent domain, what happens? 0 to 2 pi. Because omega is what? 2 pi divided by n. 2 pi divided by t. Right? So we can consider them, they change to 0 to 2 pi. Now, this form becomes xn equals 1 divided by 2 pi, coming from here, times length of 2 pi. So meaning that 0 to 2 pi, minus pi to pi, minus 2 pi to 0, whatever you want to do, length of 2 pi, that's fine. ej omega n, d omega 0. So this comes at 2 pi is given as a constant. That's a Fourier transform of discrete time case. Of course, as you define this is a reverse form of Fourier transform in discrete time. So you can view this one like that, view this one like that. What will be the difference between continuous time and discrete time in Fourier transform? Let me open that. Right here. It's page 8. We try in this chapter, we are finishing Fourier transform. So we try to summarize Fourier series and Fourier transform. Let's only have Fourier transform today. In continuous time, in case of reverse Fourier transform, they have 2 pi over 1 minus infinite to infinite e jx j omega e j omega t d omega. In case of discrete time, 2 pi over 1 will be the same, but not infinite to infinite, only 2 pi. And e x e j omega. Here, I don't know what this for is. In here, e j omega often means that this is coming from discrete time. So if you only have x j omega, that means that's the case for continuous time. If you have e j omega, x e j omega, those forms, they often refers to that they coming from discrete time. So if you see your Fourier transform is given as, okay, x j omega equals blah blah blah, that means that's coming from continuous signal. If you have x e j omega equals something, that means they coming from discrete time signal. I will re-explain this one in next lecture. However, let's try to find what this is very interesting good table comparing Fourier series, Fourier transform in the case of continuous time and discrete time case. So, in case of Fourier transform, from time domain to frequency domain, minus infinite to infinite, t, e, j, omega t. So the sequence will be quite similar. Minus infinite to infinite, x, e, minus j, omega n. So when they have a minus, this one is plus, this one is plus, this one is minus. So they're quite matching together. Maybe the only difference is this, at this point. Other than that, those integration in continuous time change to summation in discrete time, which is quite matching. Another thing, they are quite different. So in case of Fourier transform in continuous time, this x is continuous. This x is continuous, right? Fourier transform of x, which is in frequent domain, is also continuous. And both of them are periodic, not periodic. If x is not periodic. In this discrete time, it's very interesting. Both of them are discrete. This is discrete. But remember, previous page, we make this omega 0. This is discrete time, not continuous time. This frequency, we make this omega 0 find out this line. Meaning that if you don't make this omega 0, we are taking points, we are taking samples. So those are discrete. However, we make this omega 0 infinitely small to make a continuous case. So even though the original signal xn is discrete, however, its frequency domain signal is continuous. That's the one of the major difference. Also, even though this xn is not continuous, Fourier transform of it is periodic. Does not make sense, right? Doesn't make sense. However, this is a very interesting property.